Greetings and welcome to this live embedded event talk. Today I'll be talking about all things related to graphics with the Linux kernel and Userspace components. So the idea is to kind of draw an overview of all these different components and how they work together and what they do specifically. So let me switch back to my slides here. All right. First, a few words about myself. I'm Paul Koszalkowski, and I'm an embedded Linux engineer working at Vulcan. So Vulcan is a company that works on Linux kernel driver development as well as bootloader development, but we also do training, especially online these days. So if you have needs in terms of Linux or bootloader development, you can definitely call us, and we take various projects from lots of different customers to kind of help them in these areas. And Vulcan also cares a lot about free and open source software. So we try and contribute as much as possible the work that we do in the upstream projects. So personally, I've been working on the hardware video decoder for Arduino devices in mainline Linux. So this is the Sidrus driver in V4L2. I've also worked on the DRM driver for Arduino platforms, which is called Sun4i DRM. It's responsible for display. And I've also been working more recently on MyPy CSI2 support for Arduino platforms again. So that's a camera interface. And I've also developed, and I'm giving a training about graphics with Linux and Userspace. So this is the displaying and rendering graphics with Linux training. Okay, so let's begin this talk with a bit of an introduction about graphics in general. So what do we really mean by graphics? Well, first of all, graphics really deals with representing light. So this is just a way to represent pictures digitally, and pictures are really just a representation of light. So a synonym for pictures that I'm going to be using is frames. So frames and pictures really mean the same thing. So the idea is that we want to represent light digitally. So since it's digital, we have a finite number of elements that compose our picture. And so these elements are called pixels for picture elements. And the idea is that we're going to represent the colors of each pixel using numbers. So that's a digital representation again. And the way to do this is to define first what we call a color model, which is just a base for representing the pixels. So the most common one is red, green, and blue, RGB. So we have 3 channels. And then there is the color space, which is basically a matching between the value of each channel of the color model to an actual light value. So the color space is really the link between the physical world and the digital representation, while the color model is kind of a system for representing the different components of each color. Oh, so let me remove myself from this one. Now, if we want to characterize pictures, there are a few properties that we can look at. The first one and the most obvious is the dimensions of the pictures. So that's the width and the height. Then once we have these dimensions, we can calculate the aspect ratio, something like 16:9 or 4:3. These are quite common aspect ratios. So this is basically the geometry of the picture. Then there is something called the resolution, which is often confused with the dimensions, but it's really something else. So the resolution is basically the link between the number of pixels and an actual physical length unit. So for example, in American countries, that would be the number of pixels per inches. But in European countries, there would be number of pixels per millimeter, for example. Then another thing that is quite important about pictures is how the pixels are stored in memory. So there is a specific order in which the pixels are stored so that it's possible to correctly interpret the picture. So this is called the scan order. And the most common one is called linear scan order or raster scan order. And this is just the idea that we're going to read the pixels line after line in memory. So this is starting from the top. And then we have each line in memory, one after the other. But pixels also have a specific format. So the format is really the description of how each pixel individually is described. So I've already mentioned the color model and color space. So this is one thing that makes the format. Then we can also have another channel that we call the alpha channel to store per pixel transparency information. Then there is the idea of depth and bits per pixel. So the number of bits per pixel is just basically how many bits it takes in memory to represent a single pixel. So this might be aligned to a byte, or it may also not be aligned to a byte. And this will also count the alpha channel. Now, when we talk about depth, usually we exclude the alpha channel and we're only considering the actual color components. So we might have different values between the two. Then another thing that is quite important is how each color channel is organized in memory. So for example, in RGB, it's quite common that we have the red information, then green, then blue in memory, and this goes on for every pixel. But it's also possible that we have, for example, all the reds, and then all the greens, and then all the blues. So this is quite important to know if you want to properly decode the picture. Now, finally, something else that we kind of need to know to correctly understand pixels is the subsampling factors. So subsampling is generally the idea that we're going to share one of the channel information for different pixels. So this is especially useful for the YUV color models, where we have a separation between the color components and the luminance components. So luminance is kind of how bright each pixel should be. And the chrominance are the two other channels, which just bring the color information. Now, because the human eye is more sensitive to luminosity than it is to color difference, it's possible to actually use one value for a small number of pixels, like 2 or 4 pixels, in the chroma channel. So we actually have less information of color than we have of luminosity. And usually this doesn't make a very big difference for the human eye because this is just how sensitive we are. Okay, so now we kind of have some idea about pictures and pixels. And let's try to look at all the different kinds of hardware or devices that might deal with pixels. So there are basically two main categories for this. The first one would be graphics, and it contains the following things. So first of all, we have displaying pictures. So this is just using a screen like a monitor or a panel, but it might also be a projector. And the idea is just to basically reproduce light from these digital representations. So that's what we're going to be interested in at the end of the graphics pipeline. Then the second type of graphics device would be rendering device. The idea is that we want to generate digital pictures basically from information like equations or what we call primitives. So that would be points, lines, triangles, and so on. So this is what is used for 3D rendering and also for drawing in 2D or drawing fonts and things like this. So we basically have a representation of, for example, the font. That could be a vector font, which will basically give you the information of the path that should be followed to draw the font. And so then the rendering device or rendering implementation will draw the pixels that match this path. Then we have another type of thing that we can do in graphics, and that's processing. So the idea of processing is that we want to modify something in a picture, or we want to transform it more generally. So an example of this would be, for example, compositing, where we take multiple pictures and we put them together. For example, the green screen method, where you put a green screen behind someone and then you remove the green and you put a different picture instead of the green. That's an example of compositing. But also creating a single picture from the different buffers, the different pictures, the different frames of applications is also an example of compositing. There are more examples. Like scaling, if you want to resize a picture, converting, if you want to change its format, and finally filtering, which is a quite general way to transform digital pictures. So you can use it for blurring, for example. You can use it to make the edges sharper. You can use it for lots of different things. And then there is another category of things that deal with pixels, which I'm not going to mention anymore in this presentation. So that's a media part. So what I mean by media is first decoding and encoding pictures. So that could be static pictures, like we know with JPEG or PNG, for example. But this might also be video encoding and decoding with formats like H.264 or VP8, for example. Now, another kind of media thing that we can do is capturing or outputting pixels. So capturing would be, for example, using a camera. That's just a physical device that will provide pixels from the physical world, let's say. You can also receive, I don't know, like television with DVB. So yeah, all sort of things like this, which are about capturing, but also outputting. So if you want to transmit your own TV show, for example, that would be an example of outputting. So in this presentation, we're only going to focus on the graphics elements. So that's displaying, rendering, and processing. And now let's look at the hardware components that are used for these things more specifically. So first of all, let's look at the display hardware. So that's kind of important to understand later on how the software, what the software has to do and what it has to coordinate. So among the display hardware, we basically have a pipeline of different elements that are combined to kind of feed pixels, which are initially stored in a frame buffer. So that's just a memory buffer with the pixels that we want to stream to a monitor or a panel or a projector. So to do that, we're first going to use a display engine, which is really a hardware compositor. So it might take different sources of pixels, of frame buffers. Then it will assign a position on the final picture that it's going to send. So this assignment is done through what we call planes. So planes have a position, a size, and so on the final picture. So once we have a composited picture that is ready to be sent, we're going to pipe it through a timings controller, which is responsible for basically feeding the pixel at the correct rate that is expected by the other side, so the monitor. This is important to be backwards compatible with the cathode ray tube monitors, which required very specific timings to be able to drive the electron gun that would be sending the pixels on the phosphorescent screen that kind of recreates the light. So nowadays, all of the display hardware is still backwards compatible with that. So we have very specific timings that need to be respected. Then after the timings are done, and after our pixels are correctly formatted to follow these timings, we can send them through a display protocol controller. So this implements some logic to correctly, let's say, wrap or packet the pixels in the format that is expected. So for example, if you're using DisplayPort, you have to split the pixels into different packets and send them with specific headers and so on. Then we have the PHY layer, which is really the physical layer that will handle the modulation of the signal that actually goes on the cable. For example, if you're using HDMI, the PHY layer is implementing TMDS, which is transition minimized differential signaling. It's just a way of encapsulating the bits that we're going to send in the physical link, just so that it won't be prone to noise thanks to differential signaling. Then finally, we have the connector and the cable that we actually plug to the monitor. So on the pictures below, you can see a graphics card on the left, then a display panel on the bottom, and on the right, we have a cathode ray tube monitor. So usually the graphics card will include pretty much all of the elements from the display engine to the PHY. So that was for display. Now, if we take a closer look at rendering, we can basically find a number of different types of hardware to do rendering. So the most common one is the GPU, or graphics processing unit. So the idea of the GPU is that we have a highly specialized architecture with a specific instruction set architecture, which is really designed to do 3D rendering. So it can do all sorts of 3D calculation and so on. And it can also be used for 2D, as we're going to see a bit later. So this GPU is loaded with small programs that we call shaders. And it's configured with something we call the command stream, which is basically a binary series of instructions that the GPU is going to be able to understand, to correctly configure its pipeline, and eventually be able to produce pixels from this configuration. Then we have another type of hardware implementation, which is the DSPs, so digital signal processors. These are much more similar to CPUs or microcontrollers, but they also have a very specialized instruction set architecture. So it's actually quite efficient to do rendering and also processing on these. And usually they will run a specific firmware or a specific real-time operating system. Then another approach is to use the fixed function image signal processors, which are really just hardware implementations that are dedicated to a very specific task. And so in this case, unlike the GPUs and DSPs, we don't have any software running in that. It's just a purely hardware design that does image signal processing. So it's kind of common for processing and not very much for rendering. And then finally, we can have the CPU-based implementations to do the rendering and processing operations, which might use specific features of the CPU, like single instruction, multiple data, which is kind of a good fit for these pixel-based operations of rendering and processing. Okay, so now that we have some idea of the hardware that we can use for that, let's take a look at the software, and especially some specific concepts that apply to graphics software components. So let's begin with display again. So one important thing to understand is that once we have a display, we can only send a single picture to the display or a limited number of pictures that will be composited by the display engine. So it's very important that only one program at a time drives the display. Because otherwise, if you have multiple programs that try to use the display concurrently, you're going to see alternating flashing pictures that don't have anything to do with each other, and it's going to be very confusing. So just because we want continuity in time, we want a single application or program to access the display at one time. So this is why a very important component was introduced, which is the display server. So the display server is this one component that will be driving the display. And because we also want any number of applications to contribute, let's say, to the picture that is on the display, this display server implements a specific protocol for the clients to connect to the display server and to provide their buffers that they want to display. And so then the display server is in charge of gathering all these buffers and coordinating that. Now, it's also in charge of managing the input events because, as you know, input is correlated to display. So especially for the mouse, when you move the mouse, this has to be correlated on the display. And when you type in on the keyboard, you also only want a single application to receive these events. So you don't want, for example, when you're typing your password, you don't want all of the applications to receive the password, but only the one that you currently have in focus, for example. So you can see that the display server is also quite critical for security concerns. And so it's responsible for doing isolation between the different components. Then another component that is sometimes part of the display server is the compositor. So it's really in charge of gathering all the different buffers and producing a final picture to send to the display hardware. And then finally, we have a window manager, which will define the policy between these different clients. So it will say which application goes on top of which application is selected, which application is being moved, and so on. So for render now, the situation is a little bit different because we don't have this exclusivity problem. When we're rendering pictures, we can render different pictures at the same time in parallel. So this is the case with GPUs. And so now GPU rendering is based on using primitives, which I've mentioned a bit already. So these are vertices, which are just a name we give to points in 3D. So vertices, lines between these vertices, and triangles made of the different lines. So they all have positions in 3D. And so this is used to kind of create geometry and create shapes in 3D that the GPU is going to render in a final flat 2D frame buffer. So we can also use textures to apply on that geometry. And also what we call maps, which are just like textures, except that they provide internal information for calculation instead of being purely visual elements that we want to apply on the geometry. So in order for GPUs to do this rendering, we have programs, so they are called shaders, that basically coordinate what's going on. And there are different types of shaders. The most important ones are vertex shaders, which can apply transformations to the geometry in 3D space. And they are also involved with lighting. And then finally, we have also the fragment shaders, which will basically define the final color that is applied on the final picture. But there are also more advanced shaders, for example, tessellation shaders, which allow modifying the geometry in a quite fine way. So the thing to really understand is that shaders are kind of small programs that are compiled on the fly and that are provided to the GPU hardware as part of the command stream. Okay, so now that we have quite a precise idea about the different aspects of graphics and the different hardware components that are involved with graphics, let's take a look at the Linux and Userspace graphics stack. So we're going to begin with the displaying stack, so to drive the monitors and the panels. So on the kernel side, there was a first interface that was called FBDev. Well, it's actually still it still exists. So FBDev, which was kind of the first attempt to support displays. It's very limited, and it has lots of issues. So for example, you cannot configure the pipeline. It doesn't support hot plugging. It only pre-allocates buffers, which is quite a serious limitation. And it also has synchronization issues. So it's kind of hard to make changes to the frame buffer synchronously with the refresh of the display. But this is still used, for example, for the on-display console that you see when you boot up the computer or when you're using a TTY console session. So this is still using FBDev. But now we have a more advanced and more relevant interface for today's hardware, which is called DRM KMS. So DRM is the Direct Rendering Manager, and KMS stands for Kernel Mode Setting. So DRM KMS is basically the part of DRM that deals with display. So KMS is much more advanced than FBDev because you can configure each element of the pipeline separately. You have lots of flexibility in terms of how you connect things together and so on. It also has a generic UAPI, which means that basically any implementation, any user space implementation of DRM can work with any DRM driver. And it also has a flexible property-based system that can be used to kind of configure different switches and different elements separately. So it doesn't have the limitations of FBDev in terms of frame buffer management. So you can allocate frame buffers as you want, and you don't have to write to the same memory area, especially if it's being displayed. So this is great for synchronization. Then there's a quite recent API that was introduced, which is called the Atomic API. And this one basically allows grouping and synchronizing changes to the display hardware. So this can be useful, for example, if we want to configure multiple monitors at a time and we don't want to have any intermediate states. It's also useful if we want to use multiple planes, so multiple frame buffers on the same display, and we want to update these planes synchronously, and again, we don't want to have any intermediate states. So this wasn't possible before, but now with the Atomic API, this is something that can be achieved. DRM also has a compatibility layer with FBDev. So this is why you can have a frame buffer console if you have a DRM driver. So DRM will basically register itself as a FBDev driver. So you have this backwards compatibility. Now, finally, another subsystem of the kernel that is involved is TTY. So when you start up your system with the Linux kernel, initially all you have on the screen is the frame buffer console with a TTY. So that's a kind of a terminal. And if you want to start a graphic session, you have to ask the kernel to detach FBCon, so to detach this frame buffer console. So this is the graphics mode switch that can be done using some ioctl that the display server will call. And then when you want to switch between the different virtual terminals, so when you're doing Control Alt and F3, F4, F5, whatever, then the kernel is going to coordinate what we call VT switching, which is this idea that we're going to ask the display server to release the display so that the frame buffer console can basically come back and take ownership of the display. And so this allows running multiple graphics sessions in parallel. So basically, you can have one graphics session per virtual terminal. So this is quite nice if you want to run multiple display servers and multiple desktop environments in parallel. Okay, so now that we've seen the kernel, we're going to look at the user space side for display. And we're going to begin with X. So X is the historic display server project that was used with the Linux kernel and Userspace. So X11 is the protocol that is the latest version of the protocol that is in use. So it's not actually an implementation because the implementation is called Xorg. So X11 is just a protocol, but this protocol is actually quite old and quite ancient already. And so it was completed with multiple protocol extensions. So for example, X-rand-R, which allows dynamic configuration of the displays, which wasn't possible before. Before you needed to statically configure the X server to use your different monitors, for example, and then you would need to restart the server for the changes to be applied. With X-rand-R, it's now possible to do it dynamically. Then we have X-HM for shared memory, which allows avoiding copies of pixel buffers, which is nice for performance. And then more extensions. There are actually lots more than the ones I've listed here. So X uses a concept of drivers for the input and display parts. So for example, there is one driver for DRM KMS, which is called XF86 video mode setting. And there is one for FBDev, which is called XF86 video FBDev. And you have the same with input with, for example, libinput library. So X is known to have lots of limitations and lots of security issues as well. So it's really not encouraged to use it anymore. It's not really adapted to, let's say, modern day computers, even though all the protocol extensions kind of still make it somewhat relevant. But also for embedded use cases, it's often not a very good fit because it's also quite heavy and so on. So the X server is now being replaced with Wayland. So Wayland is this idea of a modern display server, which was kind of designed as a better replacement for X, which doesn't have the common limitations and issues that exist in X. So one thing is that Wayland itself is just a protocol specification. It's not an implementation. So different display servers will be implementing the Wayland protocol. And there are also extensions to the Wayland protocol, which are optional, like the XDG shell extension, which allows desktop environment integration. So the display servers that implement the Wayland protocol are called Wayland compositors. And an example of a Wayland compositor is Weston, and that's the reference implementation that was developed by the people who also created the Wayland protocol. So it's a very good way to kind of discover Wayland, and if you want to write a Wayland client or a Wayland display server, looking at Weston is a very good idea because it's really well written, it's very clear, and it also has lots of client examples. So it's a very, very good thing to look at. Now, there are also other implementations that exist besides Weston. So Sway is an i3 inspired display server using Wayland. It's using a library called WL Roots, which can also be reused to create other display servers. And then we have desktop environments that implement the Wayland protocol in their own compositors. So for GNOME, that would be Matter, and for KDE, that would be KWin. So Wayland is really, it has lots of benefits over X. It's really more secure. It has much better isolation between the clients. So you can trust that a client cannot access the frame buffer of another client, which is hardly the case with X. But Wayland is also compatible with X applications through X Wayland. So X Wayland is kind of a compatibility layer between Wayland and X. It's actually an X server that runs as a Wayland client. So even if you want to use Wayland, but you still have applications that use X and not Wayland, it's still possible with X Wayland. So the migration can be kind of transparent. And nowadays, most of the GNU and Linux distributions are shipping Wayland, but enabling X Wayland for this compatibility. So while we're talking about Userspace display servers, I also wanted to mention a few others that are less known. So there is Mir, which was Canonical's attempt at making a new display server. It was kind of a concurrent of Wayland. But this project was more or less abandoned nowadays because they have switched to Wayland like anybody else. But then there is also Surface Flinger, which is Android-specific display server. So this one is not meant to be used in GNU and Linux distributions, in traditional desktop environments. It's very, very specific to Android. But it also implements a display server. Now something else I wanted to mention is the display managers. So the display managers are just simple programs, simple interfaces that are launched at startup to allow users to log in. So this is kind of the login screen that you see. These actually run in a display server as well. So it might be X or it might be a Wayland based Wayland protocol using implementation. So the idea is that these display managers are basically going to set up the sessions and start the desktop environment for users. So now, depending on your use case, it might be a bad fit to have a display manager. For example, on embedded, usually we don't use display managers because we want the graphics interface to start right away. Okay, so now in this slide, I'm just giving you kind of a list of different libraries that can be used in Userspace to kind of communicate with the display servers. So there are some low-level libraries like libwayland client and libwayland server for Wayland, and XCB, which is the latest X11 protocol implementation, and XLib, which is the old one. So this is very low-level libraries that are not usually used directly by the applications, but instead the applications will be using graphics toolkits such as GTK or Qt or EFL, SDL. So these are graphics toolkits and libraries, well, except SDL, which is not really a toolkit, but more of just a simpler API. But the idea is that these will provide they will basically wrap these low-level libraries into higher-level interfaces that are easier to use and that also provide extra features like drawing user interfaces. So then we have the concept of desktop environment that will use one of the graphics toolkits to provide a desktop user interface as well as a number of base applications that kind of give a coherent look and feel to the experience. And finally, another important library in Userspace is Libdrm, which is basically a thin wrapper around the DRM Userspace API. So this is what will wrap the calls to the actual kernel drivers. Okay, so now let's take a look at the 3D rendering stack, starting with the kernel side. So this is also handled by DRM, just like for display. So DRM will manage the GPUs, But unlike KMS, unlike the display part, there is no generic Userspace API for the render part, for the 3D or GPU related part. So it means that each render driver in DRM has its own API that is specific to that driver. So this is because the GPUs are highly specific, and it's nearly impossible to create a generic interface between the kernel and Userspace for that. So the kernel side and the kernel drivers are in charge of a few low-level aspects, but they don't actually do so much. This is mostly I/O related tasks. So this includes memory buffer management. So these are called BOs, or buffer objects. And this is using the gem API of DRM internally. Then another task is command stream validation and submission. So Userspace will provide different command streams that will be validated by the kernel, so that the kernel makes sure that the command stream won't try to access the data of other programs, other applications. And then it's going to submit that command stream to the GPU and ask it to process that command stream. So this is done through different tasks that are scheduled with the DRM scheduler or a scheduler specific to the driver. So the idea is just to coordinate between different clients, different applications that might need to use the GPU at the same time. And so they have to be given time slots and so on. So this is for the DRM part, but usually for GPUs, there are also proprietary implementations that can exist, and these are not using DRM, they are using their own specific interfaces, which are found usually either in downstream kernels, so kernels that were modified by vendors or manufacturers to include their own drivers, their own GPU drivers, or it might be out-of-tree drivers that you can build against the official kernel and use as modules. Okay, so this is for the kernel part. Now we're going to look at the Userspace APIs for 3D rendering. So there are various different APIs, and the most common one is OpenGL. So OpenGL is in charge of providing a generic interface for using the GPUs. So this is what the applications that want to do 3D rendering are actually going to use. OpenGL is kind of a compromise between a complex interface, so it's not that complex, and the amount of control that we want to have. So it's not very complex, and it doesn't kind of offer full control over the device. So it's kind of a middle ground. And this is why it's kind of well appreciated, because it's not too complex, but it also offers most of the features that we want to use from the GPU, and it's not limiting either. So OpenGL works with a stateful and context-based programming model, meaning that if you want to do something, to do an action, it has to be split up through multiple function calls. And the function calls will have an effect that may depend on previous function calls. So it's like a context that you're building through different successive calls. Now, in order to send the shaders, it has its own shading language, which is called GLSL, for GL shading language. So this is just a language that looks a little bit like C, and that allows describing the small programs, so the shaders, that will be compiled and sent to the GPU. So OpenGL itself mostly targets the desktop GPUs, but a kind of derivative version of OpenGL was created for embedded GPUs, and it's called OpenGL-ES. So it is kind of a simplified version of OpenGL, but actually the two are fairly close. And it's not uncommon that a GPU that does OpenGL-ES is actually also capable of doing OpenGL. So OpenGL and OpenGL are for the rendering part, but something quite important with GPU rendering is also how the results, like the produced picture from the GPU, is integrated with the rest of the display stack. So this is done with an API that is kind of in between rendering and displaying, and this interface is called EGL. So it's really responsible for providing buffers that can be sent to the display components, like the display server. And so EGL provides functions that can be integrated with OpenGL API, and that will link to display server protocols like X11 or Wayland, but also Android. So there was a previous interface for X that kind of served the same purpose, which was GLX. And now it's considered deprecated. So even if you are using X11 and you want to do 3D rendering, it's much better to use EGL instead of GLX. And now finally, there is a kind of more recent API, which is called Vulcan. So Vulcan is really meant for very advanced GPU usage because it's a very low-level API that gives you very fine-grained control over the GPU. But it also means that it requires a lot more code and a lot more efforts to kind of get something out of the GPU. So it's using a direct programming model, meaning that you basically have long function calls with many arguments that kind of all specify the operation that you're doing. Memory management is also very low level. So it doesn't have the same abstractions as OpenGL. So you kind of have to be doing more and more, and it's easier to make mistakes also. And for display stack integration, Vulcan actually has its own system that is called Vulcan WSI for Windows system integration. So it doesn't use EGL. But since Vulcan is much lower level, it can actually be used to do more than 3D rendering. So for example, you can use it for general purpose GPU, which is compute. So like you can accelerate general purpose calculation using the GPU, using the Vulcan API. Now for the shaders, a difference with OpenGL is that OpenGL will take shaders in source form in GLSL, and Vulcan will take shaders in a kind of pre-built format that we call an intermediate representation in a format that we call SPIR-V. So this is kind of a pre-processed representation of the shaders, and so because it's not directly the source, you can imagine that it's faster to provide these intermediate representations, and so there is less handling and less treatment to be done by the library that compiles the shaders. So talking about this library that compiles the shader, this is the Userspace implementation for the rendering stack. So before I've only mentioned the APIs, but these APIs are implemented by a specific 3D Userspace implementations. So the free software one is called Mesa 3D, and it's really the reference. And there's basically no other free software reference rendering library for GPUs. So it supports all of the APIs that I've just mentioned. And basically, it uses the DRM kernel side to communicate with the actual hardware. So basically, each hardware that has a driver in DRM render is also supported by Mesa. So we have examples that I've listed below, like Radeon, AMD GPU, Nouveau, Etneviv, VC4, V3D, which are for the Raspberry Pi, or Lima and Penfrost, which are for the ARM Mali GPUs. But Mesa 3D also implements software backends, which can be used if you don't actually have a GPU, like a hardware GPU, but you want to do 3D rendering or to use these APIs. Then there are CPU-based implementation that Mesa provides. It can also help with video decoding acceleration, because sometimes the GPUs have specific blocks to accelerate video decoding. And so Mesa will also provide access to those blocks through APIs like VDPO, VA API, or OMX. And then finally, I've mentioned general purpose GPU usage just before. And this is also something that Mesa 3D is kind of starting to support with the Clover driver on Intel. But in the future, maybe more hardware will be supported. And this will also allow accelerating general purpose calculation through APIs like OpenGL. Now, in the case of proprietary implementations, the libraries are secrets, and the user space is always proprietary software, so we don't know what it does or how it works, and we can't modify it, and so on. Okay, so now I've mentioned the 3D rendering part. Now let's take kind of a look at 2D. So usually 2D is done with CPU-based implementations, but it's also possible to use the GPU to do 2D rendering as well. So here I've put a number of reference libraries that are used. For example, Cairo and Kia are used to do general drawing or rasterization. So this is like drawing shapes and things like this. These two are really widely used. Then there is font rendering, where there are two major libraries. The first one is FreeType, and the second one is called HalfBuzz. So these two allow rendering fonts which look really nice from basically vector descriptions into actual pixel pictures. Then for user interfaces, there are also different libraries that exist that can be used. So the first type are really the big and kind of complex retained mode drawing, interface toolkits. So that's, for example, GTK or Qt or EFL. So these have lots of functionalities, lots of widgets that you can use. And then there are more simple, which are also called immediate mode GUIs. So these are simpler implementations, and they don't work the same as the previous one because they will basically redraw the whole user interface each time, which can be a good fit, for example, for games. So you have examples there as well. Okay, so now finally, a few examples of processing libraries. So usually processing is also implemented in CPU, but it can also sometimes leverage the parallel instructions of CPUs, so SIMD. And finally, it's also sometimes possible to use the GPU for processing using specific shaders. So there are various libraries that exist to help with processing. A very common one is FFmpeg's libsw scale, which allows doing pixel format conversion as well as scaling. Another one is Pixman, that is really used a lot. It allows doing some pixel operations. And then I've also put a few other examples of implementations like NE10, which is specific to ARM processors with neon accelerated implementations, and so on. So if you want to kind of take a look at the graphics stack to have an overview, we can see on the right side, we have the rendering part. So within the example of a proprietary driver that will use its own interface between Userspace and the kernel, also its own kernel driver. Then we have the case of Mesa 3D, which will use DRM in the kernel. Then Mesa 3D might be used by applications directly, and the applications will coordinate with the display parts using EGL. So we have examples of applications that can be either native Wayland clients or X clients that go through X Wayland. Then in this case, the display server is a Wayland compositor. And this Wayland compositor is going to be using DRM KMS for the display part, and also the input interface of the kernel that is called evdev. Okay, so I'm skipping the final slide because I'm running out of time. So that's it for me. Thank you for your attention. And now, if you have questions or remarks that you would like to share, we might still have a few minutes, and I will answer them in the chat. So thanks again. And if you want to write me or just let me know of anything, I've also put my email on the slides. So feel free. Cheers.